Hey, y'all. Next, today I want to talk to you guys about one last thing in stoichiometry, and that is the concept of percent yield. Okay? Percent yield. Now, when we last talked, we were talking about limiting reactants, and we talked a little bit about why or how in the real world things are not quite as neat and orderly as in these stoichiometry problems. Okay? And with limiting reactants, it was, well, what if you end up, usually you're going to end up with more of one reactant than another, and something's going to be left over, so forth and so on. Today, we're going to be talking about percent yield. Now, this concept arises from the fact that, for reasons I'm really not going to get into, in the real world, when you do a chemical reaction, you almost always will end up with less product than you were hoping for. All right. If you go and do a stoichiometry problem, it'll tell you that you're going to end up with a certain amount of product. But in the real world, you will always end up with something less. Now, it could be because of errors in procedural errors and errors in measurement, but a lot of times it's just because the world is a very complicated place. And we think we understand exactly what the reactions are going to be, but in fact, there could be alternate reactions that go on that maybe take away some of the product as it's being formed, or it uses up some of the reactants into something else before the product that we're looking for is formed. There's, as I said, many reasons. What I want you guys to realize is, first of all, you're always going to end up with less product than you were expecting. And second of all, how to calculate for that, how to calculate, how to take that into consideration when you're doing a stoichiometry type calculation. All right. And those problems are known as percent yield problems. All right. So, few vocabulary terms. First of all is the term theoretical yield. Now, remember, we talked about before how yield, the term yield can mean, if it's a noun, it means product. Yield, product, same thing. All right. Or if it's a verb, to yield something means to produce something. All right. So theoretical yield is the maximum amount of a given product that can be formed when the limiting reactant is completely consumed. In other words, when you do a stoichiometry problem and mathematically you come up with an answer of how much product should be produced, that's the theoretical yield, okay? That's the amount of product calculated using stoichiometry. Now, in the real world, if you were then to go and do the reaction, you would get a certain amount of product. That product is known as the actual yield. That is what is actually produced, all right? And as I say, it's usually less than the maximum expected. And then when you compare those two, when you look at, well, how much actually did I get compared to what I theoretically should have gotten, we call that the percent yield, all right, which is the actual amount of a given product as the percentage of the theoretical yield. And the formula that we use, the basic calculation, is very simple. It's what you actually got divided by what you were supposed to have gotten and then changed into a percent. Okay? And remember, when you change a decimal into a percent, very simple, you simply multiply by 100, and then this percent sign, that is simply a unit. Okay? And that's how you would calculate the percent yield. Now, when you come across these problems, they come in two basic varieties. All right? The problems will either give you the actual yield and ask for the percentage, or they will give you the percentage and then ask for the actual yield. Either way, you guys are going to be calculating the theoretical yield using stoichiometry, and either way, you're going to be basically using this formula, the one I just gave you. All right? Whoops, pretend that line is under here. But actual yield divided by theoretical yield times 100 equals the percent yield. Now, this is a algebraic formula, and you can rearrange it as needed. All right. So, for example, if they are giving you the actual yield and you calculate the theoretical yield, you simply divide, multiply by 100, and that gives you the percent yield. If, however, you have a problem where they give you the percent and are asking for the theoretical, well, then you would take the percent yield, multiply by the theoretical yield, divide by 100, and that'll give you what you will actually get. All right? But regardless, theoretical yield is always calculated using stoichiometry. And remember, you use the reactant as the starting point, and the end point is going to be your theoretical yield. It is going to be that product that you're looking for, or that product that they've already given you the actual yield for. All right. So you see here, the units and identity of the actual yield are going to be the same as the units and identity of the theoretical yield. All right. So that tells you what you're going to be looking for. So I'm going to give you guys now a couple of sample problems in which you're going to see, one of them, I'm going to calculate the percent yield from the actual yield, and the other one, I'm going to calculate the actual yield from the percent yield. All right. So good luck with these. Okay, so this is the sample problems for percent yield. Now, the main formula for percent yield is that percent yield is always equal to the actual yield divided by the theoretical yield. Now, for each problem, you will always have to figure out, using stoichiometry, the theoretical yield. However, some problems give you the actual yield and ask you to solve for the percent, whereas others give you the percent and ask you to solve for the actual. Oh yes, it's also times 100. So, depending on which type you have, you're going to be either solving for the percent or solving for the actual yield. But you always use stoichiometry in order to find the theoretical yield. So, in our first problem, it reads, methanol can be produced by the reaction between carbon monoxide and hydrogen. If 8.60 times 10 to the third grams of hydrogen is reacted with plenty of carbon monoxide, and 3.57 times 10 to the fourth grams of methanol is produced, what is the percent yield of this reaction? So, since this question asks for the percent yield, we know that they give us the actual yield. And since yield means product, the fact that they give us the amount of a product means that this is the actual yield. So, we know that actual yield, 3.57 times 10 to the fourth grams of methanol divided by the theoretical yield times 100 will equal the percent. We now need to calculate the theoretical yield using stoichiometry. Now, first step with all stoichiometry problems is to balance the chemical equation. This one is simple, so we just simply put a 2 in front of the hydrogen, and that balances the equation. Step 2, we set up our starting point and end points. Our starting point is right here. It's the amount of a reactant. In percent yield questions, the amount of reactant given is always the starting point. So we have 8.60 times 10 to the third grams of hydrogen, and the question is, how much product is being formed? Now the endpoint, units, and identity must be the same as those of the actual yield. Since they tell us that a certain number of grams of methanol are actually produced, we now need to calculate how many grams of methanol were theoretically supposed to be produced. So that becomes our endpoint. We now do a mass-to-mass stoichiometry. First equality is always the mole ratio. In this, we have 2 moles of hydrogen are going to be equivalent or equal to 1 mole of methanol. The coefficient in moles of our starting point equal to the coefficient in moles of our endpoint. We now look at the units of our starting point and endpoint. Since that is grams, we need to have the molar mass of hydrogen. 1 mole of hydrogen gas, H2, is equal to 2.02 grams of hydrogen gas. We also now need to have, since that's grams, we need to have the molar mass of methanol. Well, figuring that out over here, where we have some space, we have 1 carbon, we have 4 hydrogens, and we have 1 oxygen. So those are times the average atomic mass, 1.01 and 16. So we have 12.01, 4.04, and 16. We add it up and we get 32.05. So we know that 1 mole of methanol is equal to 32.05 grams of methanol. Now that we have that, we can set up our grid. So we have 8.60 times 10 to the 3rd grams as our starting point, which always goes in the top left-hand cell of the grid. We use, since we have grams of hydrogen there, we want grams of hydrogen there. So that's 2.02 grams of hydrogen, and it's equal to 1 mole of hydrogen. Cross that out, draw another vertical line. Now we have moles of hydrogen on top. We want moles of hydrogen on the bottom, right there. So that's 2 moles of hydrogen, and it's equal to 1 mole of methanol. Cross that out. And finally, we have moles of methanol here, so we want that down here. 1 mole of methanol is equal to 32.05 grams of methanol. Using our calculator, numbers on top we multiply, numbers on the bottom we divide. So we have 8.60 EE 3. It's on the bottom, so we divided by 2.02 divided by 2 times 32.05 equals. Now we want this in scientific notation and in correct number significant figures. So we have 3 significant figures in our starting point. So we want to have 3 significant figures in our answer. So we have 6.82 times 10 to the 4th grams of methanol. Now this is the amount that theoretically should have been produced. So that is our theoretical yield. That number needs to go here since theoretical yield goes on the bottom. So that's 6.82 times 10 to the 4th grams of methanol. So now we do another calculation where we take 3.57 EE4 divided by 6.82 EE4 times 100 equals. And since these numbers go out to 3 places past the decimal, since these numbers have 3 significant figures, we round the answer off to having 3 significant figures. and the answer becomes 52.3, and we add percent as our unit. So that is the first type, where they give us the actual yield and we calculate the percent. Now in this problem, it's going to be slightly different. This problem shows us that titanium 4 oxide is a white compound used as a coloring pigment. Solid titanium 4 oxide can be prepared by reacting gaseous titanium 4 chloride with oxygen gas. A second product of this reaction is chlorine gas. So here is our unbalanced equation. To balance it, since we have 4 chlorines on the left, we simply put a 2 here, and now it is balanced. Now, the question itself reads, if 6.71 times 10 to the third grams of titanium 4 chloride reacts with plenty of oxygen in a reaction that is 75% efficient, how much titanium 4 oxide could actually be expected to be produced? Now, in this reaction, again, this is a percent yield is equal to actual yield divided by theoretical yield times 100%. Since they give us the percent, and since we always calculate the theoretical yield, this problem we are going to be looking for the actual yield. So, to rearrange this formula so that it gives us the actual yield, I multiply both sides by the theoretical yield and divide both sides by 100. The hundreds cancel out, theoretical cancel out, so actual yield is equal to the theoretical yield divided by 100 times the percent. So in this question, we have the theoretical yield needs to be calculated, but we have the percent yield. So we're going to take whatever the theoretical yield is, divide it by 100, and then times it by the 75%. And that should give us our actual yield. So now we need to do a mass-to-mass stoichiometry. The amount that they give us is a reactant. So that is our starting point. 6.71 times 10 to the third grams of titanium 4 chloride. And since they're asking for how much TiO2 could actually be expected to be produced, that is going to be our unknown. Since we're dealing with masses here, that's how many grams titanium 4 oxide could be produced. So we go ahead and set up our problem by looking at our equalities. First of all, we need the mole ratio. The identity of our starting point is titanium 4 chloride. Coefficient in front of that is a 1. So for our mole ratio, we have 1 mole of titanium 4 chloride is equal to our endpoint is titanium 4 oxide, which also has a 1. So that is 1 mole of titanium 4 oxide. Now we need the molar masses. Because this is grams, we need the molar mass of titanium 4 chloride. And because that is grams, we also need the molar mass of titanium 4 oxide. So, off to the side here, I'm going to go and say, all right, we have titanium and chlorine, 1 and 4. Titanium's molar mass is 47.87. Chlorine's is 35.45. So we have titanium at 47.87. Chlorine is 35.45. We multiply that out, and we get 4 times 35.45 plus 47.87. We get total 189.67. Once again, this is 141.80, that's 47.87, and then we add it up. So we have 1 mole of titanium 4 chloride is equal to 189.67 grams of titanium 4 chloride. Now we want to do the same thing again. We need the molar mass of titanium oxide, or titanium 4 oxide. So again, we have titanium, now oxygen. We have 1 and 2. That's still 47.87. Oxygen is 16. 2 times 16 is 32. And we have 79.87 is our molar mass for titanium 4 oxide. So we write out 1 mole of titanium 4 oxide is equal to 79.87 grams of titanium 4 oxide. And now we set up our grid. 6.71 times 10 to the third grams titanium 4 chloride. We have grams of titanium 4 chloride, so we want grams of titanium 4 chloride. They're right there. 189.67 grams of titanium 4 chloride is equal to 1 mole of titanium 4 chloride. Cross that out so we don't use that again. Another vertical line, we have moles of titanium 4 chloride, so we get those right there. It's a 1-to-1 ratio, so 1 mole of titanium 4 chloride equals 1 mole of titanium 4 oxide. And now we have one more equality, so one more vertical line. We have moles of titanium 4 chloride right there. So we put 1 mole of titanium 4 chloride is equal to 79.87 grams of titanium 4 chloride. So on our calculators, we go ahead and take 6.71 EE3 divided by 189.67 and then times 79.87 equals. We have 3 significant figures in our starting point, so our ending point will be 2.83. Again, since the decimal moves more than 2 places, it must be in scientific notation. 2.83 times 10 to the third grams titanium 4 oxide. And once again, that represents the actual yield. Excuse me, the theoretical yield, my mistake. That's the theoretical yield. And that, therefore, goes there. So we put in 2.83 times 10 to the third. All right. So we go ahead and on our calculator, we take 2.83 EE3 divided by 100 times 75 equals. And since that has only 2 significant figures, our answer can only have 2 significant figures. It also must be in scientific notation, since the decimal point would move more than 2 places. So the answer is 2.1 times 10 to the third grams of titanium oxide. And that is our final answer.